Yeah, so welcome everyone. So today I'll be doing a quick sneak peek into a talk that I'm going to be giving at DEF CON later this week, which will cover Microsoft's virtualization based security technology, or as I like to call it, virtualization based insecurity. So VBS, short for virtualization based security, is one of the most fascinating security advancements that Microsoft have implemented in recent years. It brings a lot of cool new approaches to how we can better secure Windows. How it works is it all starts with Hyper-V, Microsoft hypervisor. So Hyper-V, like any good hypervisor, has to handle isolation. So Hyper-V, when it runs VM, would never want to allow a situation where one VM can access the memory of another one. And because of this, Hyper-V implements this very tight isolation, making sure that different VMs cannot interact with one another. Now, someone at Microsoft had a very good idea over the years of taking this same principle and applying it to the operating system itself. So now, instead of running separate VMs, we can run the operating system itself on top of Hyper-V, and then use the exact same isolation technology to isolate regions within the operating system. So we can create these secure areas that even the operating system itself cannot access. So why that's useful? So it actually allows us to create new security boundaries into Windows. So before VBS, we were limited to pretty much one main security boundary, which was ring 0, ring 3. The idea was we put the operating system kernel in ring 0, we restrict user applications to ring 3, and by doing that, we ensure that users and potential attackers cannot tamper with the operating system. Now, with VBS, things get a bit more or much more interesting because we have two additional execution environments. So VBS enables us to implement what is called VTLs, or virtual trust levels. And the thing about virtual trust levels is that they provide a new type of security boundary. So the idea is that using the same isolation technology that I previously mentioned, we can make sure that one VTL cannot access the memory of another one. So what Microsoft implemented is that we have VTL 0, the least privileged VTL, which contains the normal operating system that we know already, user mode, kernel mode. Now, when we introduce VTL 1, things get a bit more interesting. Because now, VTL 0 cannot actually access the memory of VTL 1. And by that, we gain these two new execution modes, which are more privileged than the traditional ones. So we have the secure kernel mode, a more privileged kernel that can actually control the kernel and apply policies to it. And our main topic for today, isolated user mode, a new mode of execution which runs in user mode, so it is not privileged in that sense, but it enjoys the isolation provided by VTL1. The idea is that nothing within the normal operating system can access code running within IOM. So let's say even if an attacker were to compromise the entire operating system, meaning they gain full control over the kernel, they would still not be able to exfiltrate anything that is stored within isolated user mode. So this brings us into VBS enclaves. So what an enclave is essentially we take isolated user mode and we allow isolating a certain region of the process in a way that will protect it. So an enclave is a region within a process that a process cannot access. So it cannot read from it, it cannot write into it. The only thing that the process can do with an enclave is it can trigger methods that are exposed by the enclave. So, but no way to directly access it. Now, why would something like that be useful? So let's consider the following scenario. Let's say that a process handles some sort of a sensitive secret. Let's say an API key or a password. Now, if the operating system or the process itself were to be compromised, nothing will stop an attacker from simply accessing the memory of the process and exfiltrating this secret. Now, what we can do instead is we can take the same secret and store it within the enclave. By doing that, we ensure that no matter what, even if an attacker, again, compromises the entire operating system, they will still not be able to access the key, because the process itself cannot do that. What the process can do, if it wants to utilize the key, is it can indirectly use it. So, for example, we can't directly obtain the key and use it, but we can request the enclave to encrypt a certain value or decrypt a certain value using the key. So by doing that, we never directly expose the key, but we can still utilize it. So now we get to the fun part. How can we actually abuse this feature? This is a security feature that has a lot of great security applications. This is just one example that I provided. But I wanted to try to see what an attacker can do with something like this in their hands. So if you try to think about it from an attacker's perspective, if you can get malware to run within an enclave, you're probably going to have a pretty good time, because you can enjoy the exact same advantages that legitimate software will utilize, but, well, from the other direction. So nothing can access your memory, including EDRs that will not be able to scan you. And EDRs will also not be able to trace your behavior. So we get this black box where essentially we can run whatever we want. So this was the idea, at least, but it proved to be not as easy as it sounds, because you can't, it turns out that you can't just load any piece of code that you want into an enclave. There are stairs, which I go into these details in my talk at DEF CON. But now give you one example of a technique that I cover. So bring your own vulnerable enclave. Some of you are maybe familiar with the bring your own vulnerable driver technique, where attackers want to get their code running within the kernel. But the problem is that in order to load a driver, it needs to be signed by Microsoft. So what they do instead is they find a legitimate driver that is signed that contains a vulnerability. They then load this driver, exploit the vulnerability, and yeah, they get their code to run within the kernel. So what my idea was to apply the same idea to enclaves. So we can find a vulnerable enclave, load it, exploit it, and get our code to run. So yeah, the first thing we did was to try to find one, and luckily we were able to do so. CVE 2023-36880 is a vulnerability in an enclave utilized by Microsoft Edge. Now, what this vulnerability, according to Microsoft's report, says, it could have allowed attackers to perform limited code execution. So I decided to dig in to this vulnerability a bit more. And based on previous reports, I was able to see that it provides an arbitrary read-write primitive into the enclave. Meaning we can load this enclave, and after that we can write whatever we want into it and read whatever we want into it. This provides us with two very interesting capabilities from an attacker's perspective. So first, we can write whatever we want into VTL1, which, as we just mentioned, will be out of reach of EDRs. So you can put shellcode, additional payloads, configuration for your malware, anything that you want, and an EDR will simply not be able to touch it. The second thing is that the vulnerability also works the other way around. We can make the enclave actually modify the normal process memory, which also has an advantage in the context of evasion, because an EDR will not be able to, will have no visibility into any of this. So by combining these two techniques, we created a memory evasion technique that we call Mirage. Mirage essentially works by utilizing the vulnerable enclave in order to hide shellcode with a technique called sleep obfuscation. So the idea is that we spend most of our lifetime of our payload in a sleeping dormant state where it essentially does nothing, and we only wake up occasionally, execute our code, and then go back to sleep again. The idea is that during sleep, our shellcode is hidden in a way that the EDR will not be able to scan it. So what we did was we applied this approach and utilized the vulnerable enclave to hide our shellcode in isolated user mode during sleep. So let's go over this process. An attacker loads the vulnerable enclave and then exploits the vulnerability to write shellcode into VTL1. At this point, if an EDR were to scan us, it will not see anything. Our normal process is completely innocent. There's nothing bad going in there. And our shellcode is inaccessible. Now, occasionally, every couple of minutes or every couple of hours, our payload will wake up and write itself back again into user mode. At this point, it will quickly execute and then, again, override itself with benign data. What we achieve here is that we create a very, very small window of detection that an EDR cannot reasonably catch us in, because it will simply require too many resources. So yeah, for the vast majority of our lifetime, nothing happens. For a brief second, we run, and then we go back to sleep. So this is just one example of what we can do with enclaves and how we can get our code to run within enclaves. I provide some additional ones in the talk that I will be giving at DEF CON. And now I wanted to cover another interesting thing, which is what can we actually do with code that runs within an enclave. So let's say that we were able to bypass all of Microsoft's restrictions and get arbitrary code execution within a VBS enclave. So it turns out that even if we do that, it's still not going to be that easy, because Microsoft severely restricts what enclaves can actually do. So enclaves have access to a very, very reduced API sets, meaning they cannot perform pretty much all interaction with the operating system. So as you can see here, we cannot perform file operations, we cannot open sockets or perform any other networking operation, we cannot interact with other processes, registry, nothing. So pretty much all traditional malware techniques become much less trivial or simply not possible. So in the later section of my talk, I actually go into what we can still do, what we can still achieve while running from an enclave. So now I'll provide one example of something interesting that we can do, and that is anti-debugging. So it turns out that enclaves are actually in a very, very interesting situation when it comes to anti-debugging, and that is because of their location in the food chain, as we can see here. So when performing malware analysis, in pretty much every case, analysts will utilize a debugger, either a user mode debugger or a kernel mode debugger. So what we get from this is that an enclave will always be in an advantage here, because neither a user mode debugger or a kernel mode debugger can peek into an enclave or interfere with what it's doing. So if we can identify debugging and analysis from within our enclave, we can create an almost bulletproof anti-debugging method that will render dynamic analysis almost impossible. So it's not trivial to implement anti-debugging, again, because we don't have access to the normal API set, but I did still manage to find a couple of ways. So first, we have access to the normal process memory. We can manually inspect the process PEB, a structure that can tell us if the process is being debugged right now. Another thing we can do is we don't have access to timing APIs, so we can't directly measure time. But what I was able to come up with is by running a custom inline assembly code, I can measure CPU clock cycles that enable me to determine the elapsed time. And by doing that, I can identify breakpoints and other debugging measures. Now, we can take these techniques and implement a very, very evil anti-debugging scheme by doing the following. So we take some critical pieces of the logic of our malware, and we put them within the enclave. So this will be computational decryption of some sort of a value, something that our malware requires in order to run. After doing that, we'll take the same enclave routine and detect debuggers from within it. If we do that, we create an almost impossible situation for defenders, because on the one hand, they have to allow the enclave to run, because if it doesn't run, the code will not operate properly and they cannot analyze it. But on the other hand, as soon as they pass execution to the enclave, they cannot patch out anything that goes in there. So if the enclave detects the debugger, it can simply terminate the process and end the debugging session. So yeah, if implemented correctly, this technique can make dynamic analysis almost impossible. The only thing that you can do essentially is to debug the hypervisor or the secure kernel. Both activities I highly do not recommend. It's not fun. Yeah, so to wrap this up, I think that VBS is super cool technology, and it actually enables a lot of good. Here I kind of attacked it from a different angle, but overall it's an amazing feature. I think that enclaves in particular have a lot of potential from both an offensive and defensive perspective. And Microsoft is really pushing directions in the direction of enclaves. And I believe that we will see more and more organizations beginning to utilize them. And if you develop code, you should probably consider them as well. So yeah, that's it. If you have any questions, I'm here. Thank you very much.